One of its greatest strengths is speed and efficiency. Since Gaussian Naive Bayes makes strong independence assumptions, it doesn't have to compute complex relationships between features. This allows it to train and make predictions extremely fast, even when dealing with large datasets. Unlike deep learning models, which require extensive computational power and time, Gaussian naive Bayes can classify new data points in real time with minimal processing. Another key advantage is simplicity and ease of implementation. The algorithm is based on straightforward probability calculations, which makes it easy to implement with just a few lines of code in libraries like scikit-learn. It doesn't require complex parameter tuning, which makes it a great choice for beginners in machine learning and for use in production environments where quick deployment is needed. Gaussian naive Bayes also works well with high-dimensional data. Many machine learning models struggle when the number of features is very large, but naive Bayes scales efficiently. Because it treats each feature independently, adding more features doesn't significantly increase computational complexity. This makes it particularly useful in text classification, where documents often have thousands of features, words. Another major benefit is strong performance on small datasets. Unlike deep learning models, which require massive amounts of data to learn meaningful patterns, Gaussian naive Bayes can perform well even with a relatively small training set. This makes it a practical choice for scenarios where collecting large amounts of labeled data is difficult. Gaussian naive Bayes also provides probabilistic outputs, meaning it doesn't just give a classification label, but also the probability that a given input belongs to each class. This makes it particularly useful in applications where confidence levels matter, such as medical diagnosis, fraud detection, and risk assessment. However, while these advantages make Gaussian naive Bayes a powerful tool, it's not without its weaknesses. One of its biggest limitations is that it assumes feature independence, which is rarely true in real-world data. If features are highly correlated, the model's predictions can become unreliable. Additionally, since it assumes that features follow a Gaussian normal distribution, it struggles when working with data that is heavily skewed or contains outliers. So while Gaussian naive Bayes is a great choice in many situations, it's important to know when and where to use it. Next, we'll explore its limitations in more detail and discuss scenarios where it might not be the best choice. While